I'm going to start over. All right, so for today's cultural astronomy seminar, we're going to look at how do we actually measure alignments and how do we convert our measurements of alignments into declinations that we can use to understand solar alignments or any sort of astronomical alignment. So what we're going to do today is we are going to start off with the basic overview of what I spoke about earlier about positional astronomy when we did a few months ago in my two seminars. And then we're going to actually derive using spherical trigonometry, the equations. And when I say derive, we're going to use the law of cosines and do some rearranging. That's it. But we're going to show you how to use a few basic measurements to be able to calculate the declination. I'm going to have you break out Excel so you can code that into Excel. We can just add your numbers to it and it spits out the answer you need. And then we're going to do two activities if we have time. The first activity is we are going to go on to Google Earth and we are going to go to the Tonga trilithon. I'll talk about that in a minute. If you haven't been to the Tonga trilithon or seen it, it looks like this giant Stonehenge looking thing in Tonga. It's quite beautiful. And there are indications or publications that say that it aligns to the solstice. Well, we're going to check that out. We're going to test it ourselves. We're going to do the measurements using Google Earth. And then if we have time, we're actually going to go outside with compasses. We're going to try to measure. We're going to do like an example of a case of a building. If we stand at one location and we see the sun, where is it going to rise or set over a particular building? We're going to do our measurements and we're going to figure out the declination. Then from that, the day of the year that would happen. Right? It's a bit of fun. So I brought paper. So I want you to not just stare at me like most of my students do when I'm doing this. I should actually work on doing the derivations yourself. Do it with me. And then we're going to get in and start doing the coding. So it's nothing really complicated. If you haven't done mathematics in a long time, it's going to seem complicated, but it's really not. It's going to be a fair bit of review. Now, when's the last time anybody did any kind of trigonometry? 2 years ago is probably a lot closer than anybody else.
Last night.
Last night. All right. This is called trauma. Trauma bonding is what this will be. God, you don't even use trig every day, right? I'm kind of curious how many people are joining online. Not many. Everybody's like, not today. This is what happens when I send an email out saying we're going to do mathematics. The last couple of seminars, we've had a packed house. This time, everybody's like, yeah, I left my cat on the stove. Yeah. But we're going to work it out. It's going to be fun. We're erasing all the French that somebody put up here. I'm going to turn the lights on. It'd be good to actually have some light. Go. Am I falling asleep on him? So I'm going to be discussing some of the core concepts. So we're going to be talking about those before we get into doing any maths. But we did bring compasses, courtesy of Jamie.
Thanks, Jamie.
Thanks, Jamie. All right. Now I have written everything out. I could just give you this, but where's the fun in that? Everybody's going to be sitting and watching me do it. But no, you get to do it with me. We're going to go through this together. So the first thing is to understand before we do the mathematical derivation, is to make sure we're all on the same page as far as the different definitions go. So everybody knows what the horizon is, right? What do we use to measure the horizon? What's the terminology we use to measure the angles along the horizon? The azimuth, right? We measure it in degrees. So north is what? East? South? West? North? There we go. We're getting there. And for sake of argument, we're going to call the azimuth A. Capital A. All right. The altitude we're going to call H. What is the altitude? The angle between the horizon either going up into the sky or down below the horizon. So the horizon is 0 degrees. We measure from 0 degrees up to the maximum, which is 90 degrees. And what do we call that point?
I'm used to the old jams.
We're going to call that Z, right? Z for zenith. The zenith is a point directly above our heads. We're not going to worry so much about the one, but what's minus 90 degrees called? The nadir. Nadir, right? That's minus 90. So we have to give ourselves a coordinate system. We're going to measure along the horizon, then we're going to measure up into the sky. What do we call that coordinate system? We often use it for telescopes. Alt-az, right? You're not wrong. It is the azimuthal grid. It's called alt-az, right? So if you have a Dobsonian telescope, for example, the bottom just rotates, that is measuring around the azimuth, and the top just goes up and down, and that's measuring the altitude. Pretty simple. Now, when we look at our celestial sphere, there is an imaginary line that goes from north up to zenith to south, down to nadir and around. That full circle that goes around us, what do we call that circle? That is the meridian, exactly right. So when stars or celestial objects rise in the east and they come up and they cross the meridian, they culminate. As they transit the meridian, something moving across the meridian means it transits. Another term we use is that culminates. So that's the highest point it's going to reach into the sky. Unless the star never sets. What do we call stars that never set? Circumpolar stars are stars that are always in the sky. They never set. In that case, every object is going to transit the meridian twice over the course of a day. There's the upper culmination, where it has the higher transit, and the lower culmination for the lower transit.
Wait,
yes.
For the meridian is just a line, any circle. The celestial meridian specifically.
So celestial meridian is the one that goes from the poles. I mean, because I could say there's a meridian that goes from north to south that just kind of goes off at an angle. It crosses that, but this is one that goes.
Is called.
Yeah, it goes 90 degrees above, straight to the zenith. Celestial meridian. Yeah. So it goes from the horizon, zenith, due south, nadir, back to due north again. That's that line. All right. So when the sun transits the meridian, it's going to culminate. What do we call when the sun transits the meridian?
Noon.
Local noon, right? Now I say local noon. What's the difference between local noon and noon?
Local noon is exactly when it's at the highest point in the sky, whereas noon is at the time of day, which is not necessarily when the sun is at the highest point.
Right. So around the earth, we got the different time zones, and some of the time zones are artificially, because of political boundaries and various things, can be quite large. Local noon means from the observer, local noon is when it transits the meridian. However, from a time zone, noon might be an hour in some cases before or after, because you're looking at a huge swath of the earth. So it's local noon is up. All right. Which is also the upper culmination. Well, it's the culmination of the sun is at local noon. All right. So once we make sure we understand all of our definitions, it's going to be much easier to then do the derivation. So then we have that azimuthal grid, then we're going to have our equatorial grid. And this is going to be the projection of the Earth's latitude and longitude into space and all those constituent terms. So latitude is how we measure how far north or south you are from the equator. So if you're at the North Pole, what's the latitude?
90.
Positive 90. If you go to the South Pole, negative 90, right. The Earth's equator is projected into space. We call that the celestial equator, right? The poles projected into space are called the celestial poles, right? The Earth's latitude projected into space is called the
celestial latitude.
Nice try. What is your celestial latitude? Your declination, right? How far north or south it is from the celestial equator. And then, of course, you have your projection of longitude into space, which is called your right ascension. Now, what unit of measurement do we use for declination? We use right ascension, hours, minutes, and seconds, arc minutes, arc seconds. We can think about that from the prime meridian moving around towards the right. So I call it right ascension. You're ascending around towards the right direction. So a couple of other things. So we've got that system. Now, what is the ecliptic? Yes, the plane between the center of the Earth and the center of the sun. That's the ecliptic, right? Now, the equatorial plane and the ecliptic plane. G'day.
I'm good at getting lost.
I mean, we're in a different room. Sorry. It doesn't help if you're slightly dyslexic because it's 231 and 213, right? We have moved back and forth between the rooms, so you're fine. We're just going through review of terminology for positional astronomy. So it's stuff we've covered before. We're just doing a review of that before we get into the fun derivation. So the Earth's equatorial plane is angled away from, is tilted, right? The Earth is tilted on its axis, which means the equatorial plane is not going to be the same as the ecliptic plane. How many degrees is it tilted by? 23.5 degrees, right? So that means on the surface of the Earth is going to be a most northerly point where it is going to be directly connected to the sun, which means if you're at this point on the Earth and you look up, solar noon on one day of the year, the solstice, the summer solstice, will be at zenith. It will cast no shadow, right? What do we call that? What point of the year, what area of the Earth do we call it? Sorry? The tropics, right? The tropics. What's the northern tropic called? Tropic of Cancer. This other one's called the Tropic of Capricorn. Very good. So that means that everywhere between the tropics, over the course of a year, there are going to be 2 days in that year where local noon, the sun is going to be at zenith and it casts no shadow. There are going to be 2 locations on the Earth where if you're standing, there's only going to be 1 day that is at those tropics, right? Basically, the sun's you're going to get to that point, and that 1 day is going to be the highest point, and it goes back and forth again. If you're at the equator, there are going to be 2 days. What 2 days is the sun going to be at zenith if you're at the equator?
Equinoxes.
Equinoxes, right? The equinoxes, the sun will be at zenith on those 2 days, right? So we're getting our heads wrapped around this. So we have our azimuthal plane, or our equatorial plane, and that's the plane of the Earth's equator projected into space. Then we have the ecliptic plane. So we got those 2 planes that are tilted off by 23.5 degrees. Okay, everybody's happy with that? Any questions about that before we go on? Good, big question. What's an hour angle?
Related to the right ascension somehow?
Kind of, in principle. It's like students in my class. You have devices in front of you. If you don't know, look it up. What does hour angle mean? No, let's go. Let's go. It's not an exam.
Is it the amount a star would change in an hour, like the degree?
No, you're in the right direction though. It's the angular distance measured westward from the local meridian to the meridian passing through a celestial object. Right. So you can move around. Where is it there? And then you move around westward to see where it's passing through that celestial object. For example, the sun has an hour angle of 0 at solar noon. It's negative before noon, it's positive after noon. So it means by every 15 degrees, by every hour, it's going to increase by 15 degrees. Okay, well, we've got our basic concepts down. Let's start to look at what this actually is. I'm going to try to do the best I can at drawing this, make sure I get this right. So we're going to call this the horizon, right? This is the horizon here. we're going to call this the celestial sphere, or sorry, the celestial equator, CE, just for short, celestial equator. So H, the horizon. And right. So if this is the horizon here, we're zenith. Directly at the top, right here. We're gonna call this Z for zenith, right? And there's going to be an angle that goes from that down to the local horizon. And then we're going to have, is the zenith where the pole is? Is the zenith where the celestial pole of the earth is? Doesn't have to be, but it's going to be tilted off by some angle, right? We're going to call that P for celestial pole. Capital P for celestial pole. And then we're going to say we're going to have somewhere on here, it's just going to be X. That's going to be our position of an object. So object position. I've never written sideways before, but here we are. We're going to call that X. Sorry if you can't see the very bottom of it, but you're writing all this down as we go anyway, right? So there's going to be an arc between our position and our celestial pole. So we have three different arcs here. We've got this arc, and this arc. So this line is going to measure our declination, and we call our declination delta. I can hear those sighs, by the way. I'm in the room. And we're going to call again, the altitude is going to be H. So from here, the object, this is going to be little h here. This is our altitude from the object to the horizon. And the difference from the celestial equator up to this point is the declination, right? That finds that line. So what we're going to look at are some things here. We're going to call this line H. We've got this angle Q. We've got X, our position. And then we got to figure out this angle here. So what we're going to look at are a couple things. We're going to look at our co-latitude. So this is going to be the angle between the celestial pole and the zenith. We're going to call this 90 degrees minus our latitude. So in this case, latitude, I'm running out of space to write stuff.
I was like, before, sorry.
It's going to be that phi, right? That's our latitude. So that's our co-latitude. So if we're at the South Pole, what's that angle going to be? If we're at the South Pole, what's it going to be? What is our latitude? What's our latitude at the South Pole?
Negative 9.
Right. So what's it going to be? What's the angle going to be? It's going to be 0, right? What's it going to be at the equator?
Oh, we're measuring to the north. Oh, I don't know. What pole are we measuring? Any pole. Some.
We're just going to use one pole for right now. Yeah, if on the hemisphere we're on. We're not going to get too crazy with it. What if we're at the equator? What's that angle going to be? 0. Well, it's going to be 0 if we're at the poles. What's it going to be if we're at the equator? 90, right? Because what's the latitude at the equator? 0. Be 90 minus 0 would be 0. So this angle we're looking at here is going to be 90 degrees. I don't know if you can see the black very well. Use the red. 90 degrees minus our declination. That's going to be this line right here, down to this point. We've got this one, and we've got this one. So this is called our co-latitude. And that's our 90 minus 5. And then we've got our co-declination. All good? All good? Yeah.
Wait, one question.
Yeah.
What is that symbol inside the red triangle, the bottom angle?
Q, we're just calling that angle Q for right now. Yeah. And then, of course, we have this one here. This line here is going to be called our zenith distance. Which is how close are we to the zenith, right? So it's Z minus 90. Or I'm sorry, Z is equal to 9. We're calling that Z here, right? That's going to be equal to, where's my eraser? Where'd it go? Somebody could tell me it's up here, so I'm like an idiot. Well, if that's 90 minus 5, that's 90 minus delta. What do you think this is? 90 minus Z, right? 90 minus the zenith. Oh, 90 minus 8. And of course, we're going to be looking for our azimuth, which is A, right? So what we're going to do is we're going to use these 3 equations here to relate our measurements. So we can know our latitude, we can know the altitude of an object, we can know the declination, and then we're trying to find the azimuth, right? This is what we're trying to do. Hey, Tom, you came in at just the right time.
Yeah, so perfectly clear.
So our point in this exercise, we're going to be taking azimuths, right? So we're going to be measuring our azimuth on something, and we're going to know our latitude of where we're taking the observation, latitude of Melbourne. We're going to know our height, which is our altitude, the angle up in the sky. If we're looking at something on the horizon, what is it? 0, right? And we're trying to find the declination of an object. So by looking at our grid here, looking at this our sphere, we can use these 3 relationships using the law of cosines to work out an equation where we're going to be able to relate these together. That's what we're trying to do here. So once everybody has this written down, I'm going to erase it because I'm out of space already. All good? Going once? Going twice? All right. I'm going to leave these equations up here because these are the ones we're going to need. Those are going to be our relations. So our spherical law of cosines is that the cosine of our angle A is going to be equal to cosine B times cosine C plus sine B times sine C times cosine A. Everybody remembers this is trivial, right? So what we can think of is we're going to call our code. Let's get rid of that. Let's define each of these as A, B, or C. So our co-declination, we're going to call that A. We're going to call our co-latitude B. We're going to call our zenith distance C. And our azimuthal angle is going to be A, right? That's the angle at Z. Now, this is where your pen and paper come in handy. I'm giving you the equation. I don't know what COA means. Right? Plug and chug. You poor bastards.
So anything like 90 minus.
A, B, and C. A is 90 minus latitude. Or sorry, A is co-declination, 90 minus delta. B is co-latitude, 90 minus our latitude. And C is zenith distance, 90 minus our altitude. Plug those into the equation.
I can do it on the whole one.
I'm not asking you to do it for me. I know how to do it.
I don't wanna write it all down.
Jesus. It's a good exercise. That's why I've got extra paper. I've got extra paper.
Pass it around lots of paper.
Come on. I'm not asking you to do any trig yet. I'm just literally asking you to punch the numbers into that. Just take these and plug it where it says A, B, or C. That's all you have to do. What was that? Was that murmuring in the background?
Explaining what was in it.
And quota.
That last day is also the same angle or A, right?
There's a capital A and a small a. Capital A is our azimuthal angle. Because remember, we want to find our declination, which is in this term. We want to find our latitude, which we know is in this term. Our zenith distance related to our altitude, that's in this term. And then we need to find our azimuthal angle, which is in this term. So everything we need is wrapped up in this equation. If you don't remember, just putting a little dot, if the two numbers are side by side, that means you multiply them. Or you can put a little dot in, it means the same thing. Did everybody get this? Everybody's happy with that? How many people have no idea? All right. How can we simplify things?
Rearrange for cosine. Like capital A.
Well, before we get there, we need to simplify things. So we know that the cosine of 90 degrees minus x generically is equal to sine x. And we know that sine, these are just trigonometric properties of 90 minus x is equal to cosine x. So using these two relationships, you can help reduce some of that stuff down. So use these to plug in there to simplify your equation. It's always about simplifying it, right?
Either four.
I did a physics master's degree at Cosmo. How are we doing online? I've muted you and I can't see you, so it doesn't matter, but I'll mute themselves. I'll unmute you, so if you've got questions, you can ask it. I feel bad having muted you. It's kind of interesting that today Trevor's the only person who came online.
I don't count.
And Tina's there. Oh, by the way, can we give a round of applause to Trevor? He formally graduated with his PhD a couple weeks ago. Dr. Lieben, and by default, it should be Dr. Lieben or Dr. Lieben, Dr. Lieben, because I think Tina's done enough. She probably earned about 3 PhDs in this process anyway.
That's cheating.
So what is our final equation going to look like? That's our big question here. So if cosine of 90 minus something is sine, then we can just write it as sine delta equals to sine phi
Fine.
times sine the altitude plus cosine of phi cosine of our altitude times cosine of the azimuth. So now what we want to do is, for this, we can find our declination in terms of our different values, right? We know the azimuth, we know the altitude, we know the latitude. From that, we can figure out everything else. Of course, if you want to know the value of delta, how do you calculate that on this for the non-math people? Do you remember how to do that? How do you find delta here? You take the inverse sine of this value here. Inverse sine, right? So what do we have in this case if we're looking at something at sea level? If our altitude is 0, we're looking at the horizon. What happens to this term? 0, right? Because we remember that if sine of 0 is equal to 0 and cosine of 0 is equal to 1, right? So if we're looking at something where there's no altitude, we can simplify it. So, for example, if we wanted to look at where the sun is rising at the solstices, we want to see we're on the horizon. Well, if it's on the horizon, then those terms for here go to 0, and you could be able to simplify it from there. So let's try that. So we've got this equation. This is our basically, excuse me, our final equation we're going to use. We'll just have to rearrange it if we're looking for something. Call this equation 1, equation 2. Well, what I want you to do right now is say, okay, we're going to look at where the sun rises in the east. In that case, when we're doing this, our altitude is going to be 0. What would that simplify to in that case? That's right. That means the declination, the sine of the declination is going to be equal to cosine of our latitude times cosine of the azimuth. Okay. Question. I know it's a little bit hard to see for some of you because we're getting down pretty low. What is the azimuth? I'm sorry, what's the declination of the sun going to be at the solstices? We get 2 values for 2 possibilities. So in the southern hemisphere, what's it going to be? Summer solstice in the southern hemisphere, what's the declination of the sun going to be? Everybody's looking at you, Brian. 23.5? Minus 23.5, because in the southern hemisphere, our tropic of Capricorn is at minus 23.5 degrees, which means at the winter solstice, what's the declination of the sun going to be? Positive 23.5 degrees, right? So let's say we know that. So let's say, well, what's the azimuth of the sun going to be in the southern hemisphere for the summer solstice or the winter solstice? Well, we already know the declination in that case, and we know our latitude. Right now we're looking at Melbourne. We can change that for whatever latitude. What are we trying to find? The azimuth. So how would you rearrange that equation? Well, you just take divided by cosine of phi, right? That's it. Bust out Excel. Oh, a couple things I need to mention. That's important. That's for looking at an object rising, right? This works for looking at an object rising. If we're looking at the azimuth of an object setting, I'm just going to put A set, is going to be equal to 360 degrees minus A rise. So if you calculate that for the rising, the setting is going to be 360 minus that. Keeping in mind, of course, and this is not as important, but the absolute value of the declination is going to be at or equal to 90 degrees for what? 90 degrees minus your latitude. What's that telling us about a celestial object? You're in the right direction. Can't go below the horizon. If something can't go below the horizon, what does that tell you about it? This is the definition of circumpolar objects, circumpolar stars. Right. So what I want you to do now is utilizing this equation that we derived, our final equation here that gives us reference to our declination, our latitude, our altitude, and our azimuth. Let's plug that into Excel. Let's create an Excel spreadsheet. This is the great thing about this seminar. Sometimes we're just discussing historical texts, we're discussing concepts, sometimes we're number crunch. Today's the first day. What, how many months are we into the seminar series where I've got us number crunching a bit? So in our Excel spreadsheet, we need to be able to define our different terms. We're going to have our value for these things. We need to write declination is going to be what? Our latitude is what? H is what? So we did, we'll have one column that says declination. The next two, we're going to have that value, right? Then we need to have our trigonometric functions for each of those values. Keep in mind, please, that Excel works in radians, not degrees. Anybody remember the conversion for radians? All right. Well, either way. Gives us
1 degree to 5 or 1 degree.
So we'll say degree is that in radians, right? So if you write something down in your value, you're writing it down, say we're at negative 23.5 degrees. Well, within Excel, when you write that in there, before you can start doing any trig functions or calculations, you have to convert that to radians. So 1 radian would be 180 degrees divided by pi, or degrees be pi radians over 180. So make sure you account for that when you're starting to put your numbers in. So when you've got your declination and the next thing you put in the value, within that value, whatever you put in, you've got to make sure it's converted to radians. Because you're probably going to put that in there in what degrees? Well, you're going to be calculating like what's our latitude in Melbourne, for example. Sorry? 36, 37 degrees south, right? So it'd be minus 36 degrees. We can just say, we can approximate 36. You can look it up online and get the exact number. We just have to make sure that we convert it to radians.
Sorry, I don't use Excel and John is how do you put this in?
So what we're going to do is we're going to create a spreadsheet. What might help is just literally write declination. And then in space, D. Tells you what you have to define, right? So declination, declination parentheses, D. Yeah.
I don't know what the word is.
Parentheses?
Oh, that's.
There you go. You just, so you know what you're talking about. Then
Okay.
put in latitude, and then, I mean, you actually instead of D, it should be delta, you can put in your insert symbol. Ooh. Is it me or is it getting warm in here? It is hot,
That's
dude.
me sweating.
Oh. It's the heat generated from my brain's cranking, right? So there's a lot of different ways you could do it. What I think you should do is just say what your declination, and then you put a delta, and then you put your latitude, phi. That'd be 1 or 2 columns, however you want to do it. And then the column after that, you need to have your input. What's your input going to be? You can start off by putting in values you would know. So for the sun, put in minus 23.5. But remember, when you do that in there, then you gotta built in. So in your cell, you can put equal and then put the rest of your equation, and that'll do the equation for you, right? Right.
Numbers.
Work together on this. You don't have to work independently. Work with your partner, work with your peers.
So what is basically done is they're running the lag to the city that started in the so it's not really geometry, which is explained. So the curvature from the
Okay.
so that's what's considered.
That's the level that I need to start that, by the way. I think.
That's not how it's looking at. It's nice. So we did a severe solid triangle, just use a regular, so use the. So on the top, whatever was like the basics. Yeah. So this is the main thing.
See if I can plug it into our thing here, so everybody else can see what I'm doing. So I'm gonna pause the recording for just a minute, guys.
Once we solve. Wait, then I hope that's fine.
Shared my screen, no, I can't. Okay, here we are back to this. So what we're looking at here is the different values. We've got our declination, degrees, and radians. We don't know what that's going to be. That's what we have to figure out. That's what we're trying to calculate. But in our H, the value, altitude. So this is at horizon level. But within here, what I do is I hit equal and then the conversion unit, and that's what happens here. So I put in my latitude. This is set for a particular site, but just put in a latitude and we put in a particular azimuth. And then what I've done is for each of these things in our equation that we looked at before, up here, right? So we've got our sine of H, our sine of phi, so on and so forth. I've done each of those conversion units down here. Sine of H, sine of phi, cosine of H, cosine of phi, cosine of the azimuth, right? So I've just literally hit equal to sine parentheses that value in radians. And that's what spits it out. All good with that? So what that'll do is that will then help us calculate, because we're trying to calculate the declination. So then here where it says sine of the declination, we've got that value. So we've calculated that from the stuff we had before. And then we do the inverse, we get that our answer in radians, and then down here converts it back to degrees. Is everybody clear on that part? Alright. So this is just the base equation for being able to calculate our declination, right? So we're going to be using a couple of different things here. We're going to be using our calculating our declination, then we're going to calculate the solar azimuth for the rising sun and the solar azimuth for the setting sun. So what we count here for the rising sun is the value we plug into there. It's 360 minus that's going to give us our value for the setting sun. And I don't know what meaning is, but that's obviously a mistake right there. I'll double go in now and fix, because that's just slightly embarrassing. All right. And then what we're going to do here is what I've set up here. Yeah, I know we're recording. How do I get you to go away? I don't know. If I record that, it goes crazy. So. How do I get rid of that? I know it's being recorded. All right, anyway. That's so frustrating. These things come up, I can't get rid of it. So I've done the same thing. I've applied that up here, but what we're going to be looking at is this simplified equation for calculating our solar azimuth. That's all I've done right here. We're going to calculate our solar azimuth, right? So we only need to know three things: our azimuth, our declination, and our latitude. Because we're looking at where it rises or sets, so we don't need to worry about its altitude. I put those values in here, and then I've said dusk or dawn. So whether you're looking at it rising or looking at it setting. So we've got our dawn rising. I've taken 360 minus that to get that value here. All right? So I've done this for the summer solstice and the winter solstice. Okay, that's annoying, right?
So in both of these, you're solving for the azimuths? Or are you solving?
Yes. Because this, what we're trying to figure out is we're going to take an orientation of something, and we need to find out what the declination is going to be for that object. So we can also do it in such a way as, well, what is the azimuth of something going to be if we already know what the declination is? So we're just going back, if we're going to measure something, we need to figure out what the azimuth is going to be. So this is assuming we already know the declination. Summer solstice, it's minus 23.5. Winter solstice is 23.5. If you're in the northern hemisphere, they're exactly opposite. All right. Now, what I've done here is I've calculated the azimuthal range. What this means is the difference in azimuth between the winter solstice and the summer solstice. What's that angle going to be? And what you're going to find out is something very interesting. We can go through and start doing this. You start putting your latitude in at different values. So we can say here, where is it? We've got our latitude, right? And we can start to put in, so that's negative 25.6. So at minus 25.6, the azimuth range is going to be 52.5. What if I were to do this and put in our latitude as at the equator? Is this going to be a larger or smaller number, do you think? Do you think that spread increases as you go further away from the equator, or it decreases as you get further away from the equator? Sneeze. Any guesses? Archaeoastronomy, I'm teaching it, living it, loving it. What's the answer? Gets bigger. The azimuthal, the difference between summer and winter solstice, either at sunrise or sunset, is going to be the smallest where on the Earth?
Equator. The equator.
So raise your hand for the equator. Raise your hand for the poles. Raise your hand, you have no freaking idea. Tell us, I'm like, oh, what's going on? It is the equator.
Yeah.
As you get further away from the equator, that goes out. So let's try it. Let's put in 0. Now it shows that the azimuthal range, that's dusk or dawn, doesn't matter, right? So we do this at winter solstice, summer solstice. We're looking at this from the equator. That means the azimuthal range is 47 degrees. So if we look at this from minus 25 degrees, which is what we had before, you have 52.2. If we go to minus 37 degrees, where Melbourne is, it's 59. Now, there's going to be a point we get to on the Earth's surface where this number no longer makes any sense. You might know what that is. Well, it's not going to make any sense at the pole, but it's before you get to the poles.
Arctic Circle.
What can this number not get higher than? What's the limit to what this number can be? How far apart can two things be? What's the maximum separation between two things? 180 degrees, right? So at some latitude, we're going to exceed 180. Anybody know what that special definition, that boundary is called?
The Arctic.
The Arctic and the Antarctic circles, right? Which are about what?
66.67.
Minus 66.6. What happens?
Guys,
It freaks out because it's not defined. You can't go further apart than 180, right? We can go minus 66.5, but we can't go minus 66.6. Ooh. It's a bit heavy metal there, isn't it? It's a bit Iron Maiden, isn't it? It's a bit number of the beast, isn't it, right? So if we go to minus 90, of course, it's not going to make any sense either. It just doesn't make any sense, right? Well, let's go back into the tropics. We know the Torres Strait, minus 7, yeah. So what I want everybody to do is this part as well. So you've got your one side, which gives you your general calculation for anything, right? That's going to give you your declination. This is what you're trying to find here. This is your answer, your declination. This one, what you're trying to find is your azimuth of the sun at either solstice. You could do the same thing with the moon, like what's the maximum major lunar standstill or minor lunar standstill. You can do it with anything, right? Stars are going to be the same. They're never going to change, except over long periods of time. But it's the sun, the moon, the planets, they're going to be the ones that shift around a bit. But we're just keeping it simple. For the sake of our exercise, we're going to be looking at the Tonga trilithon. So before we get into the Tonga trilithon, or as we get into the Tonga trilithon, let's think about this. We need everybody to do this to put in your values. We're looking at summer solstice, sunrise, or we're looking at sunrise and sunset, summer solstice and winter solstice. So once everybody's created theirs on their spreadsheet exactly like this, we can keep going. How do I hide that stupid thing at the bottom? Does anybody know?
No, it's like that.
I wonder if that's
You cannot hide it.
I can't hide it.
Apparently not.
Jeez,
Mandatory
how
built-in
annoying is that
feature.
shit? Sorry, how annoying
It's
that's
about recording consent. So says Zoom.
Thanks, Zoom.
maybe you can just stop screen share first and then append it again. Maybe if you,
Oh, it's fine now. I'm gonna wind up spending too much time worrying about that. But good point. I just wanna make sure everybody has this programmed into their spreadsheet. They can do this themselves. I mean, if you wanna program in Python, have fun. I don't care what language you use, as long as you can do the calculation. Who still needs time? We all good? All right.
Yeah.
So the next part of this is just to do something a little bit different. What we're going to do now is we're going to pull up Google Earth. Everybody have Google Earth uploaded onto their computers? As bad as my undergrad students, I get nothing, no reaction, not a yes, not a no, not a maybe. Come on.
I don't know about Google Earth.
You got Google Earth here?
yes.
What we're going to do is we're going to go to the Tonga trilithon. So we have Aotearoa. I'm not looking at my screen. It's all right. I'll wait till you're ready. Has everybody got Google Earth up on their computer?
Yes.
Pull Google Earth up.
It's not installed. I'll use it.
Share with somebody who has an installer. Just watch me. Right? We're going to do some measuring here. I'm going to show you how to do measuring tools with this. This is really important for archaeoastronomy. It's just going to be extremely useful. In fact, I'm going to turn the lights off so it's a little bit easier to see the screen.
You don't move. It's from website.
So we can see our map here. We've got Australia, we've got New Zealand, we've got New Caledonia, we've got Fiji up here, we've got Samoa, and towards the north end of this trench about here, we have Tonga. So if you're like me and don't like cheating, I like zooming in and finding it, and I can see exactly Tonga is right here. Also because I'm a geography nerd and I just love this. Or you can go up to the right and can put in Tonga, it'll tell you. Now it's the main island in Tonga. I was here earlier this year. Quite an interesting trip. Airport's down here, the main town is up here. This area has suffered significant economic pressure because of COVID and because of volcanism that occurs up a bit further north. That's led to tsunamis that nearly half of Tonga's GDP was wiped out in about a year. So it's quite an interesting place to go, but we're going to go over here to the right side of the island. And we're going to zoom in. We're going to see these lines here. These are artificial lines made by people, right? But what we're going to look at is we're going to look down here. We're going to see the actual shadow of the trilithon. You can see quite clearly, right? So here's the shadow of the trilithon, but here's the trilithon itself. The giant corals with a coral slab, it looks like a linear piece of wood lying on top of it. That's what we see right here.
Could you zoom out and zoom back in again so I can spot that and see? Ah, thank you. Cheers.
I'm going to share my whole screen here. So I'm going to go here and share desktop. So this is what the trilithon looks like. Several meters tall, it's very high. Got that slab at the top. Now it has been proposed and been published that the trilithon aligns to the solstices. Now, what would you imagine? So the ocean is out in that direction, and you're standing here. There's a lot of vegetation in the way, but vegetation can be cleared. It might not have been there when it was constructed. But there's a history of the trilithon itself. Well, let's look at the question. Does this align to the solstices? So, what kinds of alignments would we be looking at with the trilithon? I mean, how would we define an alignment to something? What are we looking at?
Anything that appears through.
So you're saying we should be looking through it, it should appear through it. Anybody else?
It could be where it starts rising with respect to one of the pillars. It could be where it appears above the top of the plinth. It could be in any number of.
So you need a position to observe from,
To reference it.
and you need a reference starting position. So we don't know of a reference starting position. There's no clearly defined marker. There's no stone or something that says stand here. There's no X in the dirt, right? But what would you imagine you'd be looking at? Would you be looking through it like that? Would you be looking along it? Would you be under it, looking straight up? I mean, where would you imagine you're going to be observing
Through it.
through it?
Yeah.
You're probably looking through it, right? So at some point here, I'm going to look through, and like that window, I'm going to look through the middle of it, and I would expect to see the solstice sun rising through that. Either
Yep.
winter or summer solstice, one of the solstices, right? Okay. Before we go and measure anything, what are some flags coming up in your mind about this? What are some questions coming to mind?
Which is quite wide.
It's really big.
Yeah, the viewing window.
So if you're going to get down to within the solstice, you'd probably be looking a really long ways away, right? Because what you're looking at, if you're standing up to it, the angular diameter of this thing is almost 180 degrees if you're standing in it, right?
Yeah, so it's pretty good. It's pretty
Right, yeah, you can see anything in there. Our core is going to align to the soul is going to align to every part of the sun, right? And the further back you go, the angular diameter, the angular width gets smaller and smaller. Now you have to go back quite a ways
to get that.
to where you'd be looking at exactly where the sun is. We're talking a long ways away before you'd be able to get that kind. But the idea is at some point you'd be looking through it. So you're like, okay, well, let's say I stand back 10 meters from this thing, and it's maybe as far away as the end of the room is there, right? I'm looking, and the width inside is not quite as big as that room, but definitely as wide as half of that. Like where the kitchenette is, it's definitely at least that width. It's about that size. I've been there, right? So we're looking at that width. So let's say I'm standing this far away and I'm looking down at it, right? So what's the angular range of that kitchenette from where I'm standing? Everybody get up, come over here. And you remember how to use the fingers in your hands? There we go.
What are we looking at? The whole thing?
The width of the kitchenette, just half the room, that half of it for that degrees. You each work it out. What do you think it's gonna be? So, put your hand at full length. I know this looks dodgy. Don't use your right hand. Don't use your right hand. Or you can do it like this. Your little finger's about 1 degree.
Yeah.
Your 3 fingers like this is about 5 degrees. The full fist is about 10 degrees. Your metal horns, not like this, but spread out, are about 15 degrees. And your full surfer hand is about 20 degrees.
That's about 15 degrees.
For me, it's about 15 degrees from here. It's pretty solid 15. Good, thank you. Sit down. I can just imagine people looking in from the other room, we're all back here zig heiling the bloody kitchenette.
Yeah. They've already run security.
Yeah. How you end up on the stop youth letter.
Not the way you want to be.
Yeah.
So we're looking at a 15-degree range along the horizon. How wide is the sun? Angular diameter of the sun? Half a degree.
Yep.
Right, so what does that tell you right away?
It's 30 times the diameter of it, so it's.
30 times that, right? Now we remember when we're talking about the sun's position, when the sun goes from solstice to solstice, each day it's going to be at a different position, right? the difference in the azimuth between one day and the other is not equal throughout the year. As you're close to the solstices, the difference is very small. It's almost in the exact same spot for several days around the solstice. It's slow and then it moves really quick right in the middle as we come into the equinox. That's when the difference is the greatest. And it slows down as we get towards the solstice. So it does this, right? It's the same as if you see a pendulum. Right? It slows down, stops, and comes back. But its fastest is when it's straight down. It's the exact same principle. Just imagine it tilted on its side. Right? So what does that mean? If we're looking, let's say it is near the solstice. Let's say the solstice is right in the middle of this thing. We're going to be watching the sun for like half the year. I mean, or not half the year, but a long time, right? So how would you even define whether it aligns to the solstice? It's kind of a weird one. Doesn't really make any sense when you think about it. But let's assume for the hypothesis is that this aligns to the solstice sun. So how would we measure that? How would we go about, we're going to make a measurement to see if it aligns. How are we going to do this measurement? Can somebody give me an answer?
Try for the middle of the object.
So we're going to look at the exact center of it, right? So halfway, and we're going to look at what, 90 degrees to that? Straight out and see if that aligns. That
Yep.
might make the most sense,
Yeah.
right? So let's go back to Google Earth. How are we going to do that on Google Earth? Because when we look at this, we're looking at a shadow of it. So how could we do something here? Well, before we do anything, I want to show you something really, really useful. Go up to this tool that looks like a ruler, and click on that. And see over here where it says length, just click kilometers and go down to degrees. We're going to move this up here, which means if I press on that point and then move it around to any other point there, this is my heading or my bearing, or what's it also called? Give me an A. Or azimuth. The heading, the bearing, azimuth, it's all the same thing, right? This tells us our azimuth. Okay. It's going to be kind of tricky trying to figure out how we're going to do that here. We could put it here and try to get it through the middle, but it's kind of hard to define exactly what that is here, right? What's something else we could try?
You can measure across the top of it and work out the center point.
How about we go here and measure along the lintel at the very top, right? So that I think we can get a pretty decent measurement of. Look at that. That's going to vary a bit. Now, what do we do when we take measurements? We always just take one measurement and go with it? What do we do? We take several measurements and average them out, right?
Yeah.
So let's go to this thing. So I can say one measurement here, that gives me 118.25 degrees. I go back and I try it again. Oops. I try to get this lined up again. Try to get it so it's lined up quite nicely. This time I'm getting about almost 116 degrees. I do 5 or 6 measurements and I average them out. So everybody do that. However it is you want to do it, try to figure out the best way it's going to work for you. That's a better measurement there. I've got our pen and paper. So we take at least 5 measurements of this. You want to keep that bearing in the same direction. You don't want to do one going this way and then one going back the other way. That's not going to make any sense.
Anywhere across the top.
Yeah. You're trying to figure out the best way that you can measure across the lintel here. You can either go this way or you can go this way, but we're going to talk about what that means in a second. So either take 5 measurements going in this direction or 5 measurements going in that direction. You decide how you want to do it. We're trying to measure across the lintel. The lintel is the thing that sits on top of them. You see them on stone. Sorry?
How do you spell that?
L-I-N-T-E-L.
Yeah.
Not lentils, lintel.
Lintel.
It's like a lentils but backwards. Lentil. So in your spreadsheet, put in different categories, each of your 5 or 6 measurements. Then you find the average of them, calculate the average,
190.
equals sum parentheses, highlight those, divide it by 5 or however many measurements, you got that?
One more, that's enough.
But remember, that's not the bearing we're looking for. We're trying to find
How many degrees to that?
that one. So what are we gonna do? We're gonna take that number minus 90 degrees. Or if you do this direction, if you measure it that way, you're gonna take that plus 90 degrees, right? Okay, so that's gonna, if we take this value, well, we've got our alignment along this direction, so we might as well, we've got that recorded. We take minus 90 to get this direction. Or if we measure that way, we take plus 90, either way. Now we've got that direction through the center of that. So we have our azimuth.
27.
We can plug our azimuth into our equation. But remember, there's still one thing we haven't written down yet. And what is that? Our latitude. Our latitude is behind this freaking sign down here. Minus 21.1365. You want to get all the digits they've got here? Minus 21.136521. I mean, you get that many decimal places, it doesn't really matter, but it's minus 21.1366. That's all the precision you really need here. And of course, we're looking at azimuth, we're looking at declination, and we're looking at altitude. Now, if we're measuring the sun at the summer solstice, what's the declination going to be? Summer solstice in the southern hemisphere, which is where Tonga is, what's the declination of the solstice sun at summer solstice?
Minus 23.5.
Minus 23.5 degrees. We have our azimuth, which you just calculated here, and we have our latitude. You got everything you need to know. Simply plug those in and it should spit out your answer. Well, if you're looking at this equation, you only need those 2 factors anyway. All you need is your azimuth and your latitude. Your altitude 0, it's going to tell you the declination. What you're trying to see is, does the declination that corresponds to that direction match your rising sun? That's what you're trying to find out. So we've just taken a bearing, an azimuth. We know our latitude. And then, I haven't put the numbers in for that here. Those numbers are actually right here. Hello, Jack. We're in the middle of the seminar. Where are you? All right, well, tell everybody hello. Sorry, what was that?
Hello.
Jack says he's sick. Okay, no worries.
Sorry, I completely forgot you were in a seminar, but I've been all day.
Yeah, no worries. We're doing all your fun favorite parts here. We're doing calculations.
Average, so we're saying average.
And my popularity levels just plummeted quite dramatically.
So if we go azimuth,
All right, look, I'll call you back in half an hour.
Cheers. So if we want to convert it to degrees. So degrees every.
So what we're, this very simple test, you know, I've done this here for the Tonga trilithon, put the numbers in, but you know,
To be small, like.
all we're doing is we measure our azimuth, we know our latitude, we know the altitude is 0, we're trying to find our declination. We should spit our number out. Does that number
So
equal
basically 90 degrees.
the solstice? We can test for either the winter solstice or the summer solstice. What did I say it was? It was
So then.
What have I done?
minus 21.1366.
Just.
And what did you calculate for your azimuth?
2.049 radians.
Converting it back to degrees?
1.7.
27.
27, right? That's what I got for this one.
Oh.
That gives me a declination of around 56 degrees.
Minus.
Right.
Good.
Now I've calculated my solar thing for minus 21.14. More decimal places for that. 21.136.
So when you just convert these to wherever it says
This tells me that the azimuth of the rising sun
and then they're saying where it's.
at the summer solstice is going to be 115 degrees, but at winter solstice it's going to be 64 degrees.
Either way.
Do either of those match 56?
6 years, anyway.
No, it's not even inside the.
No.
No.
You can see why. They couldn't do it in Greek as well.
So does that hypothesis hold up?
No,
No, it doesn't.
not even. It doesn't point at the sun.
It doesn't point at the sun at all. If you look at through the center, it's no, it doesn't.
50 languages, so.
Fair enough.
In fact, where it points, 56, this is your winter solstice. This is the northernmost point that the sun gets is 64 degrees. It's not even pointing towards the sun at all.
No.
So if you look through it, it's not even in the solar range.
No.
Right. So where did this hypothesis come from? So what was our original measurement before we added or subtracted the 9 degrees? Remember we were here?
So we're looking through it.
Just to the limit, so 118 degrees. Let's just look at 118 degrees. Let's just say our azimuth is 118 degrees. What does that give us?
Do the exact opposite.
Minus 26.
Once was 30.
It's still not giving us anything.
X on its own, because it's 4 times X, and then divided by 4.
It's not even in the range.
So then that cancels it out. So then you have X.
So, you know, what are we taking away from this?
It doesn't have anything to do with solar.
So y equals
Well, I mean, it kind of points towards
so we
the,
got 30 minus 7
if you look down the
times 2.
If you look down the lintel,
lintel, you kind of see the summer solstice, I guess.
Minus what, 14? 16.
Right, so what's the bearing of the summer solstice? 118 degrees roughly. We're seeing 115 degrees, so within a couple degrees.
So that would be what?
It seems to be this direction. If we look at it down here, it seems to almost be aligned to the summer solstice in this direction. Does that make any sense?
No,
Not
no,
really.
unless you're really tall.
No, general tall. You might see it.
What are those pots they built?
Sorry?
Are the pots that are built in front of it?
Well, that's just it. They're past the building.
What are they supposed to represent?
I don't know. There's,
Like sites of stuff?
yeah, I think it's their own imaginations of what they think this is supposed to be. And there are a couple stones back up in here, but they, it's not clear from the lines to anything. So what you could say, maybe it doesn't align to the sun, but maybe it would align to a star, for example, right? Maybe it was the rising of a particular star. Maybe it was a rising of the moon at its, these are things you have to look at. I mean, if you've got no cultural context, you don't know anything, right? But let's just look and see. It's going to align to something, right? Because something always arises on the horizon. Are there any bright stars that rise in that direction? So we have an azimuth at 27 degrees, right? That corresponds to a declination of 56.2 degrees. Well, let's pull up bright stars. Do any of them have a declination of 56.2 degrees or something close to that? Keeping in mind, of course, it doesn't mean it was aligned to do that, but we're just having a bit
So
of
it
fun.
says Canopus has a declination of approximately negative 52 degrees. Is that too far? Plus,
Well, let's look. We're looking at stars that have a declination of around 55, 56 degrees. We don't need to use stellarium, we just need to look at 20 brightest southern hemisphere stars and see what the declinations are. That would be northerly stars, of course, because we're looking towards the north.
Well, we're looking for about 56.
Akana.
Yeah, Achenar is about minus 52. Alpha Centauri is about, well, no, it's minus 60. Well, about minus 60.
Yeah, minus, because we're in the southern hemisphere.
It's not gonna be super bright.
Although he's got
Right.
Declination around. Keep in mind, it's giving us a declination of 56 degrees. Not minus 56 degrees,
positive 56 degrees.
positive 56 degrees. Remember, zero declination means it's along the celestial equator.
All right, that makes sense.
So it's a very northerly star, because we're looking at an azimuth that's only 27 degrees. We're looking at a very northerly azimuth, right?
Right.
I mean, you can tell when you're looking at this thing, it's very much tilted towards the north, right?
Says there's no bright stars with a declination of exactly that.
Not exactly, but what's in that range? What's in that 5 or 10 degree range?
So Capella,
See, look here, this is straight north. You have to make sure the northern thing is straight above, right? This is looking really high up towards the north. So it's going to be a northerly star, right?
Does it have to be a star?
No.
Is it major?
Right now, all we're doing is speculating. All we're doing right now, we've tested the Solstice hypothesis, it doesn't stand up. So we're looking at saying, if this thing, if, is the biggest boldface, underlined, italicized, red, colored if, it links to something astronomical, what could it link to? What are some of the brightest stars or constellations that rise? Could it be the moon at a standstill? Well, what's the declination of the moon at the standstill? You should be able to look and see pretty quickly and pretty easily. But from what we calculated here, an azimuth of 27 degrees corresponds to an celestial object that is going to have a declination of about 56 degrees.
So, Alpha Cassiopeiae, I pronounce that, is 56 degrees.
Well, here's one.
Capella major.
Sorry?
This control F and put 56.
All right, we're getting somewhere. I'm gonna do this. That didn't work.
So this one here is just, this is only if you want to do architectural alignment stuff, really, but so this one here is.
What about
Say, for example,
major lunar
and
still
that would be like
declination?
0. So h would equal 0. So then sine of 0 is equal to 0. So it'd be whatever this
Positive
is.
28.5 degrees. Does that fit in with our data?
So h was 0.
No.
Times 1 times cos A, so just drop out and become cos.
So it doesn't tie to the lunar standstills.
In this case, that would be declination is something from cos. So then we just change cos A to be.
It's exactly double of
Yeah.
the lunar standstill.
Yeah. But yeah.
The whole point of this exercise is for you to understand how to calculate different things. It's meant for you to, if you get a bearing or an azimuth and you know its altitude, then you can calculate what an object's declination would need to be for it to be seen at that spot. Right? We've done a very simple one where there's no altitude. We're looking at the rising sun at the solstices, and we're checking a particular site. The hypothesis that the Tonga trilithon aligns to the solstice, I'd say is busted. Unless you're saying that along the lintel it is, which I don't know why you would observe the sun across the lintel, it literally blocks your whole view. Maybe the sun would rise above that, but I don't understand why you would even do that in the first place.
It's still a pretty wide object to rise above.
It is. And there's nothing indicating as to why that should even be the case. Now let's look at the history of this thing, because that's something we want to look at.
Sorry, I think plus 28 to minus 28 degree equal to 56, right?
That's a spread of 56. That's the major and minor lunar standstill is the range, the azimuth range will be 56. That doesn't mean it's not a declination of 56. So it would need to be at 56 to minus 56 for that to be the range. So
There's no obvious sighting.
Haʻamonga, a Maori means a bird in a Maori, sorry.
There's no obvious like sighting point.
No. Well, let's look at the history. So it's got it's a stone trilithon located in Tonga. Okay, we know that. It's sometimes called the Stonehenge of the Pacific. It is just over 5 meters high. It's 1.4 meters wide, thick, in this direction. And it's 5.8 meters long. So from here to here, it's 5.8 meters. From there to there is 1.4 meters, and it's 5.2 meters high, right? It's about 30, 40 tons. It's very big. So near the trilithon is a stone called the stone to lean against. It was believed that the king was seated with his back against the throne. He was safe from assassins who may sneak up behind him. But this is a stone that's a little bit further away. According to traditional accounts, the monument was made by the folk hero Maui, as the stones were thought to be too large for mortals to handle. Maui was supposed to have obtained the stones from Uvea Island and then carried them to Tonga on a giant canoe. Historical analysis places its creation around the year 1200. So what is special about that date 1200?
Approximate date of the voyage to Aotearoa.
Yeah, that's about the date that, you know, the Iwis went to Aotearoa, you know. There had been people there before that, but that was the first concerted effort to really migrate there, right? Big voyages, right? So it was seen as a gateway to Hecata, or the royal compound, blah, blah, blah. Astronomical significance. In 1967, one of the kings came to believe that this had an astronomical significance, telling position of the sun, solstice, sunrises, and equinoxes. This theory is supported by research of the Tongan historical Tavita Fale. According to Tavita Fale, there's a V-shaped mark on top of the lintel that aligns with the rising of the sun during the solstices and the equinoxes. C.F. Velt, an astronomer at another institute, disagrees with the findings of the king and argues that the V on top is an arrow directed along the main axis of the lintel, only 10 centimeters long, too short to be any reliable indication. Plus, the thing is really high up. It's 5 point something meters. So you have to climb up to the top of this thing and look at a 10 centimeter arrow. Does that make any sense?
No.
No. No. That's where the hypothesis came from. But yet, when you read the literature, it talks about how there's this big Stonehenge in Tonga that aligns to the solstices. It even says that on the sign that I went and visited. And I'm looking at this being like, on my phone being like, what? This is nowhere near where the sun would be. So here's some of the historical images of it. Suspense. It's quite jagged still. What the hell? It's like a 10 gigabyte file or something.
Where's the arrow? Up there?
It's on top of it, apparently.
Pointing at the solstice.
So would you say this hypothesis is supported or rejected?
Rejected.
I would say it's pretty firmly rejected.
Interestingly, if you look from the aerial imagery, and it's hard to say because the imagery doesn't go back that far, but there's a series of avenues that span out radially in towards the ocean, and they are at certain angles. So if you zoom right out, you can see that there's one that's kind of following the alignment of it, and then there's multiple others in rays going towards the ocean.
Those are contemporary ones that have been built in because they're trying to show how it aligns to the solstice and the equinox.
Right.
This would be the solstice line here. This is the equinox line. This is the solstice line. Now, if you look at that, of course, you can get any three lines can converge onto one point because you're observing from any one place. That does not look like it's aligned any of them to me.
No.
I mean, it's like a 180 spread.
Yeah.
I mean, if it was used and it's constructed around the time of navigation, I'd be interested to know how it ties to navigational stars if it was tied to any, which is probably,
Could be. Now, curiously,
I mean, it's facing.
we did say that along this direction here, this is roughly along the solstice direction, which means they built this avenue. They've actually constructed the town along the southern edge. This road actually marks out the solstice. At summer or winter? Which one? Summer, right? Because it's more southerly here.
Yeah.
So they've artificially built alignments into the structure of the town itself, at least the limits as to how far it can go into that. which is quite interesting. But there's nothing to indicate that it actually aligns with the solstices at all. Right? So the other exercise that I wanted to give you guys to do was to actually go out, instead of going on a computer and measuring something, would be to go outside with the compasses and measure something. You go outside and you say, okay, if I stand here looking towards the west or the east, there's a building, there's a top of the building here. What declination is going to correspond with that? Where the sun's going to rise at that point or set over that part of the building. You pick whatever one you want. As long as it's in that range, it's going to be some point, and they got to figure out what's going to be and then when it's going to be. That's a fun little exercise.
Okay, whether the Chancellor's office actually lined up with the solstice or something like that.
That's right. And you can actually use this to measure your actual altitude, which is a pretty cool thing to do. Now, we've got 15 minutes. There's probably not a lot of time to go do this, but we're going to go out and we're going to give it a go anyway. So, 2 teams of 4. Let's have fun. I want you to go outside. I want you to find in the easterly or westerly directions. I want you to, from where you're standing, find a building that has a tall, prominent feature and figure out the declination that the sun needs to be for it to peer over that, either when it's rising in the east or setting in the west. That means you need to get an azimuth of it and you need to get an estimate of how high it's going to be, its altitude. If you don't have the altitude meter on here, you're gonna have to use your hands and approximate it. And then we're gonna come back in, plug it in and see what we come up with. All right. 1, 2, 3, 4. 1, 2, 3, 4. How do you want to do it?
What did you say?
The Tonga island chain. Well, there, all.
Ah.
Take your time with you, they'll be able to come back. It'll get longer than 15 minutes. But I need these back. So I'm giving team A this, I'm giving team A one of these. I'm giving team, and who's the team B? All right.
You can do your makeup while we're doing it.
Go collectively take your measurements, be rigorous.
Be rigorous. Good time for the.
All right, guys, we're gonna finish
I'm gonna
that.
find out whether your office aligns with something in there.
Well, there's no windows in this, so.
Okay, so we've got rid of the
See ya.
sun start.